So I want to talk about the graph of the tangent function, just to amplify a little bit what's in the book. It's going to be pretty similar to what they say in the book. So let's look at what the computer gives us if we put in y equals tan x, and we graph that. And instantly we can see some things about this. It looks like it's periodic. Looks like the same pattern is repeating. Let's check that by zooming out a bit. So I'm going to zoom out in the x to like minus 15 to 15. Looks like the same pattern repeated over and over and over again. So that's interesting. Well, let's find the period of that then. Let's go back a little bit. Let's go back to like minus 5 to 5 where we were before. And it looks like here's one pattern, here's another, here's another. Looks like they're all copies of each other. So it looks like going from here to here is one period of the thing. That I go from any one point to an exactly corresponding point. Notice that with sine and cosine they hit twice, and you can't go from just one 0 to the next 0. But if you go from this uphill 0 to this next uphill 0, it looks like that really does complete one pattern. And lo and behold, it looks like pi, a little more than 3. So our guess is that the period is going to be pi. And we can check that more carefully later. So let's just put that in. Period of tangent equals pi. Now that's a pretty good guess. It would be very strange if it was wrong, and it does turn out to be correct. Now, one thing that's very different about this from sine and cosine is this function seems to blow up. It seems to go really high, and it seems to be not connected together, or the technical term is it doesn't seem to be continuous. Whereas sine and cosine is a nice wavy function that you'd never have to take your pen off the paper to graph it. This is doing something really weird right in the middle between 0 and pi. Well, it looks like probably right in the middle, maybe at pi over 2, it looks like it's doing something weird. Well, it's the kind of weirdness we've seen before with rational functions, and that's an asymptote. So let's just check. What I'm going to do is I'm going to zoom out in the y variable. Let's say go minus 20 to 20. Now that sort of squishes down the part in here to make it look a little bit different, but it's still the same idea. And now we see, yeah, it looks like it's going up, and we don't see any reason why it's going to stop right at 20. And so it looks like it's going up as far as it wants to. And indeed, it looks like right about 1.5, or maybe a little bit more. So probably right at pi over 2 is where it's having that asymptote. So we can check. We'll check that in a minute for sure. Asymptote. Vertical asymptote at x equals pi over 2, and of course it's going to repeat that at pi over 2, and then it looks like if I add pi to that, yeah, the repetition, the periodicity is going to do that. So pi over 2, 3 pi over 2, 5 pi over 2, etc. And for negative ones too, it looks like minus pi over 2, etc. So here it is, minus 1.5-ish, or minus pi over 2. So that would be our guess from this graph. So let's go back to a better scale for this a little bit. Let's say minus 4 to 4, and let's say minus 3 to 3. Let's try that. Okay, so we can see little bits of the other patterns, the periods, but it's mainly just one period of this function. And I want to talk about why the tangent has this shape. You can do it in terms of sine and cosine, sine divided by cosine. You can do it in terms of y over x, or opposite over adjacent. I like to think about it in terms of the slope of a line. So here's another picture. I've got a unit circle, and I started out here with a line. This is a line at 45 degrees. And that has slope 1. If I go a certain amount over, I'm going exactly the same amount up. If I go 1 unit over, I go 1 unit up. The slope of that guy is 1. And the slope of a line is the tangent of the angle that line is sitting at. So that's telling us that the tangent of, well, let's see, 45 degrees. We don't want to use degrees here. We're going to use radians. It's a much more natural unit. Tangent pi over 4 is equal to 1. And we knew that. That's one of the things we know about tangent. We want to be really good at memorizing that, but that's definitely something that's not totally new knowledge. Well, let's see. what happens if I get closer and closer to pi over 2? That's going to be the most interesting thing, because this seems to be telling us, this other graph seems to be telling us that as the angle gets closer and closer to pi over 2, that tangent increases. So let's see what the picture is there. The picture is just that if this line gets steeper and steeper in terms of slope, or rather, as the angle approaches 90 degrees or pi over 2, it's going to get steeper and steeper in terms of slope. So let me just quickly draw in a couple of those. Let's kind of add, let's add something that we know will have high slope, like y equals 5x, and see where it ends up. Yeah, so this is something where the angle is getting close to pi over 2, and the slope is getting very high. It's getting somewhat high. It's 5. Let's do one more. Let's say y equals like 20x, or let's say 10x. It's hard to tell after a while. We don't want to get too much. So there's 10x. And that's this new line here, that if the slope is 10, the angle is quite close to pi over 2. So as this thing rotates, I like to picture this as a line that's actually actively rotating up. And as it rotates up, the slope goes very, very high. And the slope eventually becomes almost well, basically as big as you want. Okay, so let's look at a couple of other things. Let me add a couple more in. Let me add in y equals minus x, slope minus 1. Where does that sit? This is this new line here. You can either think of that as rotate pi over 4 in the clockwise direction and get slope minus 1. Well, that would say tan of minus pi over 4 equals minus 1. Or you can also get that line by starting here and going through pi over 4, 2 pi over 4, which is pi over 2, to 3 pi over 4. So that's 3 pi over 4. That's also equal to minus 1. And so this is exemplifying some of the behavior of tangent. The fact that these guys are opposite, when I negated the inside, that turned out to negate the outside. That's suggesting, but does not yet prove, that it's an odd function. So here's a conjecture. Tangent is an odd function. Let's think about that geometrically. It says that if I crank this angle up clockwise, I'm going to get a certain number. Counterclockwise. If I crank exactly the same amount counterclockwise, I should get the negative of the slope. Well, let's try that. I've already put in like y equals 10x. I'll put in y equals minus 10x. We'll try it one more time. This is not proving it, but it's suggesting it. And I'm comparing this line down here with this line up here. This line, if I go over a certain amount, it goes down a certain amount. If I go over that same amount, its brother up here goes up the same amount. So these two lines have negative slopes compared to each other. And if I think about it in terms of their angle, this was achieved by going a certain distance, a certain angle up counterclockwise. This is symmetrically going clockwise. And so it looks like we have the characterization of odd, that if I change the angle to negative, then I change the tangent to negative. Well, let me show you the algebraic proof of that. So I've been focusing on the geometry here, either by the circle or letting the computer do the graph, but let me finish up by connecting it to how you could think about with this algebraically. You can definitely think of tangent theta as sine theta over cosine theta. If you want to, in principle, if you understand sine and cosine well enough, you understand tangent. So I'm just going to plug in that definition negatives, and I'm going to have to hurry to go get under the YouTube limit, and use the fact that a minus sign comes out of the sine. So this is a little bit sophisticated, that I'm using the facts that I know that sine is odd, so a minus sign comes out of that, and cosine is even, so no minus sign comes out of that, and then I just repackage it, and I see that it really is minus tan theta. So that's a proof, really, that tangent is an odd function. And I'll stop there.